So, welcome back to this class. In the last class, we talked about fluorescence resonance energy transfer, or FRET. We talked about the use of fluorescence for glucose detection. Prior to that, we talked about the SPR technique, surface plasmon resonance. Today, in the same line, we will move to another technique, which is called optical polarimetry. What really optical polarimetry is about? Now, optical polarimetry take advantage of the concept of chiral molecules. I hope you guys remember the chiral molecule from your high school. Please revise what are chiral molecules. I'm pretty sure all of you know, but just revise. Molecules that can rotate the plane of polarized light. This is the definition of chiral molecule. Okay. Glucose is a chiral molecule. So, if there are no other chiral molecule, then glucose can be detected easily. As such, it can rotate the polarization plane of light beam by an angle alpha in a clockwise direction. The amount of rotation is proportional to the concentration of the analyte. Okay. The optical path length, the temperature and the wavelength of the laser beam, which is usually somewhere between the upper region of the NIR, near infrared, and lower region of the optical band, which is around 780 to 400 nanometer, and that is the basic principle of optical polarimetry. Now, unfortunately, minimal optical rotation associated with the physiological level of glucose, the presence of other active molecules, and the high degree of light scattering in the skin and tissue makes it unfeasible to use optical polarimetry in skin. So, skin is out of question. So, unlike SPR, where you have a sensor on top of a skin, it is not possible in skin. But, however, it is possible to use it on aqueous humor in the anterior chamber of the eye. So, if you look at the structure of the eye, it is something like this. So, you have the retina sitting here. So, this is your retina, this is your optic nerve, these are the ciliary muscles, here you have the lens, here you have the cornea, and here you have the aqueous humor, and here, sorry, one more thing, here you have the retinal pigment epithelial cell, which is called the RPE, retinal pigment epithelial cell layer, and here you have the aqueous humor. Okay. With this anatomy, it is clear for you, right? And you can always refer to any book to see the structure of the eye, everything will make sense. The method consists of polarizing the light emitted by the light source before reaching the eye. The reflected light is then analyzed to determine the angle of rotation alpha and intensity. Such technique has the potential of detecting a small amount of glucose as long as tissues such as sensitivity to temperature, motion and others can be addressed positively. Now, that brings us to a very interesting point. There is a disease called diabetic retinopathy. Because of the diabetes, it leads to damage on the retina. Such thing happens because the blood vessels, so behind it there are blood vessels which are supplying blood to the eyes. These blood vessels have higher pressure. These higher pressures, because of the diabetes, they damage these tissues, and because of the damage, you see the glucose infiltrate into the aqueous humor. So, when you can use or you can fine tune this optical polarimetry for eyes, then you really can address the problem of challenge of diabetic retinopathy in a much more elegant manner. While skin is challenging so far because of lot of scattering of light, but eyes is far more easy. So, you have to throw the beam and it should be able to say you how much glucose is present here, and that is exactly how it works. So, here you have the light source which is falling out here. So, here you see the lens, here you have the cornea. Now, here is the sensor and the analyzer is sitting here. So, there is a polarized light, unpolarized light, it is passing through a polarizer and it is hitting, and that angle alpha you are analyzing, and that angle is proportional to the glucose. This is how the optical polarimeter works. Now, from here we move to another optical technique, because there is a lot of love for optical techniques because most of them are non-invasive. So, you see this is a NI technology, non-invasive technology. Now, what is optical coherence tomography, OCT? OCT is an imaging technology based on the principle of low coherence interferometry with coherent radiation that is capable of detecting changes of the optical characteristics of the biotissues at micrometer resolution. Despite being initially developed for tomographic imaging of the eye, it can nowadays measure glucose concentration through the skin with acceptable accuracy and specificity. So, you realize optical coherence tomography now could be used on a skin, unlike optical tomography or optical polarimetry. So, how some of these optical techniques are helping to bypass the challenges with the traditional way. So, this is how it works. There is a light source, okay. There is a beam splitter, goes to the reference mirror, there is a scanning mirror on beam splitter, and here on the skin surface. And here is the ISF, here is the glucose molecules standing there, and this is where all the detections are happening. So, OCT is another emerging powerful tool for continuous glucose monitoring, but of course, they all come with you need really advanced instrumentation at your disposal. So, that is what I was mentioning in the class. Miniaturization is pretty a key move. The smaller your this whole setup is, better your device sellability will be. The technology consists of radiating a skin with coherent light with a wavelength of 800 to 1000 nanometer. The backscattered radiation generated is then combined with a reference to produce an interferometric signal that is sensed by photodetector as shown in figure. So, there are a lot of backscattered signals which are being detected. Hence, if an increase in glucose occur, it will increase the refractive index. This is the important part for you to understand. So, there is an increase in glucose level, it will increase the refractive index of the system and decrease the scattering coefficient, and this will lead to decrease in the scattering coefficient, creating a mismatch reduction of the refractive index between the medium and the reference proportional to the glucose concentration. This is in principle the basic way of understanding optical tomography for glucose detection. Okay. Then comes the near infrared spectrum. This is a popular technique, but it has its own problem. NIR, commonly they call it near infrared spectroscopy, not non-invasive here. Near infrared spectroscopy needs relies on the absorption and scattering of wavelength in 780 to 2500 nanometer range due to molecular vibrations. We have already talked about this in the previous classes. Now, I am just revising through and rotation of bonds inside the molecule. It uses three basic measurement modes: transmittance, reflectance, including difference in reflectance, and interactance. However, they all rely on the same core technology, the dispersive spectrometer. In transmittance mode, a scattered light irradiates polychromatic light onto the sample. As you could see, this is the NIR, polychromatic light, scattering plus absorption on the sample, diffraction grating, and it is going to the detector. Okay. This is how the one type of them works, which is a light source irradiate polychromatic light onto the sample, and a diffraction grating on the other side split the transmitted radiation into constituent wavelength before being sensed and analyzed by a detector and a computer respectively. In reflectance mode, which is the part B of it, which is out here, it is slightly different. What is happening in reflectance mode is the diffraction grating and the detector are on the same side of the source to detect, because there is a reflection happening, detect the specular reflection, the reflection at the definite angle from the sample. Similarly, so if you look at it, so here it passes through, here you see it is reflecting, and here you have the diffraction grating. Here it passes through, then you have the diffraction grating. You realize the difference. So, this is the reflectance mode. Okay. Now, there is a third one, which is interactance mode, also senses the reflected light from the sample, but it uses a light barrier between the incident and the reflected beam to separate the field of view of the detector from the illuminated area. Let us explore this one, where you have same thing. This is also on the reflectance mode, but there is a separation, because and this helps in reducing the noise of the system. But interesting part is all the modes are suitable for measuring absorption, transmittance, and scattering in the sample, and the preference from one of them is based only on the type of media. For example, transmittance mode is preferred for analyzing fluid and very thin transparent sample, whereas reflectance and interactance mode preferred with dense, solid and thick samples. So, when we talk about reflectance and interactance mode, we are talking about skin, whereas these are more like clear fluids or much more translucent fluid, you can use them, or thin tissue slices. So, depending on it, these technologies are being developed. Now, when we talk about mid infrared spectroscopy, we talked about NIRS, near infrared spectroscopy. Now, we talk about mid infrared spectroscopy, also called fingerprint spectroscopy, is a vibrational spectroscopy technique. Hence, it relies on the same system configuration and absorption principle of NIR spectroscopy, but use it in the middle of the infrared region, approximately between 120 terahertz to 30 terahertz. Although some claim 12 terahertz to be lower limit of the frequency band. Due to longer wavelength, there is less scattering of MIR radiation in the tissue, leading to higher absorption rate and specific sharp absorption lines in the spectrum, especially between 8 to 10 micrometer. The characteristics means that the molecule have unique spectrum in the MIR region, making it ideal for molecular identification. Unfortunately, Now, these are the challenges. Strong water absorption in this region does not let MIR signal to penetrate more than some micrometer into the tissue, 100 micrometer approximately, making necessary the use of powerful MIR sources such as quantum cascade laser, which are also called OCL lasers, and use of complementary technologies such as photoacoustic spectroscopy. We will come to that one, to increase the sensitivity towards glucose detection. So, water is a big challenge. So, always remember, when we are working on the aqueous system, which all the living forms are in the aqueous environment, where water is the major molecule on which everything is suspended, these kind of spectroscopic challenges are rampant, because water has a very peculiar absorption zone, and different kind of waters, depending on how smaller the water concentration is, there are a lot of changes which occur in their properties too. So, you have to take into account that there will be interference from water molecules along with the other ions which are present in water or entrapped within water. Okay. So, next we have again discussed this, but we are just kind of going through it. As I told you, is Raman spectroscopy. This is another very favorite technology which is being used. Raman spectroscopy or scattering determines the decrease of scattering of monochromatic light based on Raman effect. When single wavelength light hits a target, it produces scattered light traveling in all directions. The majority of this radiation, called elastic or Rayleigh scattering, we have already talked about Rayleigh scattering earlier, and has the same wavelength as the incident light, while the rest is just a small amount of scattered radiation with a different wavelength called inelastic scattering, represent or Raman scattering. So, we are talking about the inelastic or the Raman scattering. Such a wavelength difference is the Raman shift, and it represents the difference between the initial and the final vibrational state of the molecule under study. As such, Raman spectroscopy is dependent on the rotational and vibrational state within the molecule, and it can be used to detect specific absorption bands and quantify the corresponding molecule, meaning that peak location in the Raman spectrum shown in the vibrational mode of each functional group within the molecule. Hence, the indicating that the Raman shift expressed in wave numbers will be same regardless of the wavelength of the incident light. In case of glucose, the most representative vibrational mode are linked to OH-CH stretching band around 2900 and CO and CC stretching band between 800 to 1300. So, when we talk about viewing the Raman spectra, these are the numbers you have to remember. And the corresponding stretches which are happening at that zone. Okay. As long as, so whenever you get the Raman spectra, if you look, there is that peak, that means it contains possibly contains glucose, but then you have to have the other measures which can tell you this is how it works. And when you look at, this is how the Raman spectroscopy works. There is a monochromatic light, and these are the different kind of reflections happening, but we are only talking about the inelastic. This is such wavelength differences in Raman shift and represent the difference between initial and the final vibrational state. So, we are only talking about scattered radiation with a different wavelength called inelastic scattering, and this is what Raman spectra gives you. So, we are only bothered about these red ones, and this is where you see the wave numbers will be there, and that is where you are going to see. Now, there you have to remember those three numbers 2900 and 800 and 1300. So, you have to locate where they are standing, depending on, you have to make a call that is the sample contains glucose and how much it contains. So, you realize again this comes with a sophisticated instrumentation, and all these detection tools are exceptionally challenging in terms of the sophistication of the optics, and there are certain basic disadvantages with Raman. The basic configuration of Raman spectrometer consists of a lens capturing part of the scattered radiation. As you could see, this is the lens which is carrying part of the scattered radiation, and the directing it to the filter which is out here, the filter which is filtering out all the Rayleigh scattering, and let only the Raman scattered light to be sensed by the detector. The computer does the processing of the signal and provides the corresponding Raman shift. Unfortunately, interference and instability issues prevent Raman spectroscopy from providing accurate glucose measurements in vivo. So, you realize while this is one of the very beautiful technique, I personally love this technique, but the amount of interference, the amount of ambiguity really prevents for a in vivo. So, you have to realize that you have to put something on the skin and you should be able to get a data. Such things without damaging with any kind of light what you are putting on the surface or throwing on the surface is extremely challenging, even with the most powerful tools like Raman. And this is something which humanity will keep trying, how we can really get this or set these detection limits and how far we can go with all these things. So, still we have few more of these technologies we will be discussing in the next class, which are of course, will be starting after this with the far infrared spectroscopy, and then we will come to a few other things. But for the timing, realize that a lot has to be done. We are just talking about one molecule, glucose, which is the simplest of all. But when we are talking about the biodefense systems, there are tons of them, and each one of them needs a unique signature. It may take 50, 100 years before we have concrete systems. So, please focus, think through, because this is where the maximum literature is there with glucose. So, that this will help you to understand the holistic approach. When you finish this course, you should have a very holistic approach about the biosensors development and the opportunities what it is going to provide you. Thank you.